This is the AP Stats Chapter 2, Lesson 2 outline on normal distributions. So I want you to leave this video knowing what does it mean for a distribution to be normal, capital M, capital N, and how can this provide us with additional information about our distribution. Well, let's look at this key question to start. Normal has to do with shape. It will always be bell-shaped, which is also symmetrical, meaning if I put a mirror right down here along this line facing either side, it would look like the second half. So we have symmetry, meaning the mean equals the median. When we have this symmetry, there's only two things I need to know about my normal curve because it's bell-shaped. It's mean, which is what it's centered around here. Due to its symmetry, that's also equal to its median. And its standard deviation, which is the distance to the change of curvature on the slope here. So you can see getting more steep right here. It's about as steep as it gets before it begins to decrease in the slope to be less steep. So that's the spot you know that one standard deviation is. Now I like this here because it's more detailed. We do approximate, so the 68 is these two areas in the blue. 68, 95 is within two standard deviations, and 99.7 within 3, you can see down here. We generally just chop off the end of those and call it the 68, 95, 99.7 rule because it's easier to remember. Again, that's an approximation, which we'll use a lot of approximations this year, as long as they're close. A lot of times, due to chance, what we end up with, even if we were more exact, would be an approximation too. So let's look more at all the things we can learn from the normal curve. So first off, we're looking at a type of density curve. That means 100% of the values lie underneath. Or if we're talking proportions, that's 1. So the entire area under there is equal to 1 or 100%. Sometimes is an easier way for students to think about that. That means that it is entirely above the x-axis, and it's specified by two things. It's mean, mu, and standard deviation, sigma. We can use a capital N, parentheses, the mean, comma, standard deviation to describe shape, center, and spread of a normal distribution. Standard deviation is the distance from the center to that change of curvature point that I mentioned. Here's the abbreviation I want you to use when you're doing a problem. Here is an awesome link to a normal curve and proportion calculator. I also put this in the comments of an update that I posted on Schoology, so you can just click there on that. That will be helpful for your free response and also as a way to visualize this. I also posted one additional one. It's a new link than this one. It's posted in Schoology from the textbook company that does something similar. This interactive normal curve's a little better, so you should try going there too with your free response. Now, the interactive normal curve does a lot of cool things here. It draws our normal curve. Right now it has z-scores labeled. And that's because z-scores always have a mean of 0 and a standard deviation of 1, because we subtracted the mean from every value and then divided by the standard deviation. So remember those transformations to center and spread. We can look at z-score values, or if I have a problem and I had a mean of 12 and a standard deviation of 1.2, I could say I want to know how many values are above. Let's look at what one standard deviation would be, 13.2. Above, and it highlights the area for me. This is much what we're going to do in the plan step of our problems, is sketch this out and shade the area of interest. It calculates that area for me, so 15.87% of values are greater than that. So this is very useful. And it's in that link there. Remember, it's also on Schoology in an update that I posted. We'll come back to this in a second for our free response question. So we could either have a big standard deviation, which would be a shorter curve that's wider, or a small standard deviation that would give us a tall curve that's skinnier. Both are normal, just different standard deviations, both centered around the mean. And you can see that right here is that change of curvature point that I mentioned. Here it is on this curve. And that's one standard deviation. So you should start to get the feel where a z-score of 1, 2, and 3 are. And down here, that's represented by the mean plus 1 standard deviation, so z-score of 1, mean plus 2 standard deviations, mean plus 3. So you should be able to use those interchangeably, that's what a z-score of 3 is, 3 standard deviations above the mean. And there's our 68, 95, 99.7 rule, just using the approximate values. You should know and be able to apply that. You should also be able to take that a step further and say, okay, if 68 are within the mean minus 1 standard deviation to the mean plus 1 standard deviation, then about 34% are in this area between the mean and 1 standard deviation. So you should be able to do those types of breakdowns with it. You should also say, okay, if 68% are within 1 standard deviation, that means 100% minus 68% or 32% are outside of it. So this whole tail and this whole tail. And because it's symmetric, this tail all the way up here above a z-score of 1 is about 16%, half of 32%, and this tail is 16%. So you should be able to go back and forth with those. So another picture in your text is nice that you can reference. And just a note that if a distribution is normal, once we turn it into z-scores, that distribution still is normal, because remember, shape doesn't change. Whether we add, subtract, multiply, or divide, and z-scores, we're subtracting the mean and then dividing by the standard deviation to every value in the distribution. So if a distribution is normal, its z-scores are normal. Okay, here is your multiple choice question. So pause right now. It's what does the 68, 95, 99.7 rule tell us about a normal distribution? Feel free to go back if you need to. Look in your 2.2 summary, and then answer A, B, C, D, or E, whichever one of these 5 you think best describes the 68, 95, 99.7 rule. So one more antiquated way to do things, an older way to do them, was to use a table. So we had a table of values that told us the areas for certain z-scores. So it would tell us the percentile. So if this area is shaded, so it'd say at this z-score, here's the percentile, or the percent of values in this distribution that are less than that z-score. So table A has z-scores and their percentiles. We're going to need to know how to do it this way. We're going to also use the calculator. And generally in the class, I'm going to want you to do things on the calculator, but give you the option both ways. When we do these problems, we're going to state, plan, do, conclude. I'll show you what's entailed in each of those steps for this. Here's a quick overview of what that is: the problem of interest, plan with the drawing, do the calculations, and then conclude. So here's a question to take you through the whole step, and then this will also build to your free response. There's a manufacturing company that makes metal plates, and they have a mean of 16.1, a standard deviation of 0.3, and they're normally distributed. I can express all that right here. If plates are less than 15.5 centimeters, they're not usable, as they won't cover the length. We want to know what proportion are too small to use. We're going to state and then state the problem. Here I've stated that problem and given the appropriate information that it's normal, the mean, standard deviation. We're going to plan by sketching it and labeling the values. There's 16.1 the mean, there's a z-score of 1, 2, so on, and then 15.5, and I shade the area I'm interested in, less than that. So I know this should be a small value. If I got an answer up at above 95%, I might have found this value by mistake. We know this should be a small value. I am then going to do the calculation, find the z-score, and use my table or my calculator. You can put in the z-score and then go to second varse, normal CDF. Low bound, just put a very small number. The upper bound, 15.5, that we're interested in, and then the mean and standard deviation. I could also put in the z-score, low number, -2, and then mean would be 0 and standard deviation would be 1. And I get about 0.023. You'd get a slightly different number using the approximation, but close, 2.5%. So we'd say we'd expect about 2.3% of the metal plates manufactured to be too small to be usable, given that they'd be less than 15.5 centimeter, and the plates follow a normal distribution with a mean of 16.1 centimeters and a standard deviation of 0.3 centimeters. So your question is going to build on the same one. So go through your calculator and do this before you answer your question, so you can go back on the do step that I just did. Metal plates that exceed 17.1 centimeters are also too large to be usable. I'd like you to sketch that out right now. You can go back to the curve that I had for you, but now we're looking at greater than 17.1 centimeters. So for your free response, I want you to describe the distribution, the z-score for 17.1, and then the proportion of times that we'd get a value greater than 17.1. Go back to that calculator function and use it, or you can use that applet that I gave you online. And we'll go over how to use your table when we do this in class. To use the applet, just pop in 16.1 and 0.3, and then you'd be looking instead of below, you'd be looking at above and put in the value of interest, or you can go to second varse, normal CDF on your calculator. Okay, we don't want to assume a distribution is normal, so we're going to look at the 68, 95, 99.7 rule as a way to do that. Should be bell-shaped, should be unimodal, should follow that rule, no multiple peaks, or it's not normal. You don't have to worry about normal probability plots, that's not on the AP. So again, go back on my example. This is much like the example. Sketch it out on paper for yourself before you answer, and then submit your answer. Click send me a copy of my responses so you have a copy. Review 2.2 in your text. Go over the outline online in Schoology and the vocab. And then go ahead and submit your work.